Okay, so now to solve this problem. So the first step we want to do is we want to treat the uh, entire structure as one structure. We don't care about what's going on inside of it yet because we want to find the reactions. That's our very first thing we're concerned with. So let's just treat this thing like a one long beam. So we can draw a beam that's the length of the bridge, and at A we're going to have an upwards reaction. We'll call that R A Y, and then we're going to have an 1,000-pound force downwards, which is 25 feet away from RAY. And then we're going to have, at U, we're going to have an upwards reaction and a sideways reaction. So we're going to have RUY and RUX. And again, this is going to be 25 feet times 6, which is 150 feet. And we treat this as a simple finding the reactions problem. So we're going to take the moments. So this is point A, this is point U, and this is point D. So we're going to sum the moments about point U. So we're going to say the sum of the moments about U is, we'll take positive to be counterclockwise. So we see RAY is causing a moment about U in the clockwise direction. So we're going to have negative RAY times the distance, which is going to be 175 feet. And then the force at D is causing a moment in the counterclockwise direction, so it's going to be positive. So we'll have the force, which is 1,000 pounds, times the distance to U, which is 150 feet, equal to 0. And if we solve for RAY, we get 1,000 pounds times 150 feet divided by 175 feet. And if we put that into our calculator, we get 85.71 pounds. Oh, you know what? I'm sorry. I put 100 times 150. That should be 1,000 times 150. So we're off by a factor of 10. And this will be 857.1 pounds. Okay. So we could go ahead and find the reaction at U, but in this case it's not necessary because we're using method of sections. With that, I'm going to go ahead and start talking about how we're going to split up this structure to find the force at CF, because that's what at the end of the day, that's what we want to find. So the method of section says that you can cut any structure like a truss right through the structure, and as long as you don't cut through more than 3 members, you can treat whatever you cut as a separate equilibrium problem and find any of the internal forces that you cut through just through that equilibrium problem. So in this case, and again, the section that you cut does not have to be a straight line. So in this case, let's cut through the truss, or the bridge. Let's cut through right here. So we've gone ahead and we've just sawed off this section of the bridge. We're going to throw this section away, and we're only going to keep this left-hand side. So if we draw that left-hand side now, we're going to get something that looks like this. And I'm not going to use a straight edge here, so forgive me. But it's going to look something like this here. So we're going to have that, and we're going to have forces. So right, because we've cut through CF at the top, we're going to have a force that replaces CF, because whatever members we cut through, we replace by forces. So we're going to have F sub CF. That's the force that was from, that's the force that is inside member CF, but we've cut it through now, so we're going to look just at the force. And then we have a force that was in member EG that we cut through. So we'll say F sub EG. and we have a force that was in member DG that we cut through F sub DG. So again, we've replaced all the members that we've cut through, which are we've cut through member CF, we've cut through member EG, and we've cut through member DG. We're replacing all of those members with forces. And those forces are in the same direction as those members because we know the direction of the members. So then we also have a reaction at A that's applied here, and we know that because we just found it. So this is going to be 857.1 pounds. And we also know that an 1,000-pound force is applied here, 1,000 pounds. Okay, and then also just to put some names on these, we know that this is point A, B, C, and then we know that this is D and E, just so we can refer to them easier. Okay, so now we've gone from this problem like this. It's a pretty complex bridge with a lot of members, but really we're particularly concerned with CF. Maybe we know for a fact from experience, we maybe know that this is a highly stressed member. We maybe know that this is corroded, and we want to determine what the maximum force in this so we can see if it's going to break or not. Maybe we know that it is the most problematic member in the bridge, so we're only analyzing for CF. So we've gone from this big problem and we've reduced it down to this tiny little equilibrium problem here. So we can actually treat this now as a rigid body, so we don't even have to worry about what's going on inside of it. So we can, just to show that, I'm just going to kind of fill it in a little bit here. And now we have a 3D, not a 3D, I'm sorry, just a 2D equilibrium problem. And we know this force and this force. We don't know these forces, and we want to find this force. And actually, just to show that these forces are going to meet at point G. We didn't draw, but these members are going to meet at point G. So, in order to find force CF, we're actually going to take the moment about this point G. So, the sum of the moments about G, and we're going to take the positive to be counterclockwise, is equal to 0 because we are not moving. And we also know that these two forces here, FDG and FEG, are passing through point G. They're going through point G. Because of that, they cannot cause a moment about point G. So we can just ignore these when we're looking at the moment about G. And again, I'm sorry, this is 25 feet, this is 25 feet, and then this is 17.5, 17.5. So again, FEG, FDG are not causing a moment about G. So we're going to now find the moment about G. So FCF is going to cause a moment in the clockwise direction about G. So it's going to be FCF, negative FCF because it's clockwise, times 2 times 17.5, which I believe is 35, yes, 35 feet. And then we're going to have 1,000 pounds, which is going to cause a force in the counterclockwise direction, times 25 feet away from G. And then we're going to have a moment caused by the reaction, and I'm just going to draw it right here, plus, and actually this is going to be minus because this reaction is causing a clockwise moment about G, 857.1 pounds times 50 feet equals 0. And if we solve for FCF, we see that we get so we're moving everything over, or we're moving FCF over. We see that we get negative 510.1 pounds. So we're not completely done yet because we see that we got a negative result. So our assumption of FCF, the force going this way, is incorrect. So now we know that it's actually going the opposite way. So now we have to kind of think about, okay, so now that we know it's going the opposite way, how is it going to be in tension or compression? And the way we can think about that is think about the force, or think about the member CF acting upon this equilibrium, acting upon this structure. So if FCF the member is pushing this way against this equilibrium, it must mean that if you're looking at the member FCF, it must mean that it's in compression. And I guess I can show that a little better if I draw a little picture. So we have our cut that we made, and we know that FCF is actually going this way. So then if we draw the member FCF, we must know that the force in FCF is equal and opposite from Newton's third law. So it's actually pushing inwards, and if we have two forces on a member pushing inwards, that means the member is in compression. So we can say the force in CF is equal to 510 pounds in compression. So we'll just put a C there, and that is our final answer. So hopefully you liked this case study of this bridge in East Windsor. It's there. There's actually a hiking trail that goes right under it. I would suggest checking it out. I wanted to go there and make a video of it, but unfortunately I was a little too busy. Still, it's still there. Has been there for 100 years, so hopefully you can check it out. And thanks for watching.